Okay, you can construct a orthogonal set of vectors from a linearly independent set. They by themselves need not be orthogonal, but you can always construct an orthogonal set of vectors from a linearly independent set. Okay, so it is possible to construct a set of orthogonal vectors from a set of linearly independent it is possible to construct a set of orthogonal vectors from a set of linearly independent vectors. Okay? This procedure is known as Gram-Schmidt orthogonalization. This is called Gram-Schmidt orthogonalization. This is essentially like a computer algorithm. Step 1, step 2, step 3. How do you do this orthogonalization from given set of linearly independent vectors? So let u1, u2, etc. un be a set of linearly independent vectors, but not orthogonal. From u1, u2, un, I am going to construct another set v1, v2, vn, which are orthogonal. So how do we do that? In first step, I will call v1 is equal to u1. So first vector I will take as it is. First vector I will take as it is. Okay. My second vector, so it is going to be like it's a construction procedure. I must have my second vector such that it is orthogonal to this vector. Okay? So, my second vector, I will take u2, okay, u2 plus a constant times v1 I will take and demand that this constant be so chosen that this is orthogonal to this. Is it clear? So what is the demand I will put? I will put the demand as v2 comma v1 is equal to 0. But what is v2 comma v1? v2 comma u2 plus alpha times v2 comma v1. This has to be equal to 0. Sorry. v2 comma u2. So I will ask this v1 comma v2 is equal to 0. So v1 comma u2 alpha times v1 comma v1 is equal to 0. Correct? So this implies I must choose my alpha as v1 comma u2 divided by v1 comma v2 with a negative sign. If I choose my alpha in this fashion, so I am going to write this as u2 minus v1 comma u2 divided by v1 comma v1. Remember, this is the only vector, so maybe I will write this vector symbols to be Clear. So V1 vector is U1 vector. V2 vector is U2 vector into, this is the inner product, this is a scalar, this is a scalar. So this is the only vector. So interpretation is very simple. You have U2. What is U2 V1? This is the overlap of vectors U2 and V1. You subtract from that overlap, then whatever remains is non-overlap, that is whatever is orthogonal. So in that sense. Now V3, I have to choose, this should be, this should not any overlap with this as well as with this. So it is in the same lines. I will argue that this is nothing but you take the overlap with V1 by V1 into V1 and take the overlap with V2 by V2 So in general, you can define a Vn which is equal to Un minus sum over j is equal to 1 to n minus 1 Vj Un divided by Vj comma Vj. By construction, V1 and V2, V1, V2, Vn are orthogonal. This is called Gram-Schmidt orthogonalization procedure. So, is there any doubt in the construction? U3 along V1 because I want it to be orthogonal to V1, so I take the projection along V1 and subtract it. I take projection along V2 and subtract it. What will remain is orthogonal to V1 and V2.